Exhaustive BM25 wastes time scoring documents that can never win. MaxScore shows how to skip them while keeping Top-k Retrieval accurate. This is the workflow you'll know how to run when we're done, which ranks documents by skipping low potential scores and returns the top matches. I'm Professor Pi, teaching search and IR with simple Python. MaxScore Top-k Retrieval is a practical trick to cut wasted work in a ranked search. Normally, we run BM25 over every document that contains a query term. That's correct, but often unnecessary. Thousands of candidates never make the top. MaxScore asks, can we skip scoring some documents and still get the exact top K? In real use, this saves CPU and latency on medium-sized corpora, especially for multi-term queries. The method is built from two simple moves. First, compute conservative upper bounds on how much each remaining term could possibly add to any document score. Second, evaluate the must-have contributions first and only touch optional postings while a document still has a chance to beat the current threshold. The outcome? The same ranking, but fewer score computations. We will build a small, self-contained example that shows BM25 scoring, derives per-term caps, marks essential terms, and finally runs the MaxScore loop to prune work. The toy corpus is compact, so you can check numbers and watch the savings. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To start, we load a tiny document set, tokenize into counters, and compute document lengths and document frequency for every token. That gives the raw counts we need for BM25 IDF and length normalization. This snippet stages a compact lexical corpus so we can reason about MaxScore-aware BM25 later in the tutorial. It enumerates doc texts into the counter-based docs mapping, letting doclen capture token counts that feed the K1 and B normalization factors once we start scoring. The dictionary comprehension that populates term DF counts how many documents contain each token, giving us the document frequency signals that the upcoming IDF calculation will wrap in math.log. Because we print average doclen, you can read the exact 4.33 token baseline. Lengthening the third document would push that average upward, and every later BM25 denominator would inflate accordingly. Now that we have doc lengths and document frequencies, we need a baseline full BM25 pass to see true scores and the cost of exhaustive evaluation. This gives us the reference top K and the number of scoring touches to compare against. This example turns those corpus statistics into actual BM25 scores, so we have a reference point for MaxScore pruning. The comprehension IDF multiplies math.log across term DF, after which K1 and B set the saturation curve that doc norm caches per document. Inside the nested loops, we accumulate contrib per document query match, counting exhaustive ops, so we know the cost of evaluating every candidate term. Finally, sorted X yields top IDs and the gap between the first and second scores. Increasing K1 would flatten weight and shrink that gap, while decreasing B would favor shorter documents. The printed line shows Doc2 narrowly leading Doc1 with a 0.18 margin, earned at the price of 5 scoring touches. With full scores in hand, we can compute term-wise upper bounds, which tell us the maximum a term can add across documents. Those upper bounds let us decide which terms are essential to reach a current top K threshold and which are optional. This code derives the MaxScore bounds we need to decide which query terms are truly essential. Term upper walks every docs posting to record the largest possible contribution per term under the same K1 and B configuration, while baseline MCS captures the current Kate score from the exhaustive pass, sorting into bounds, and peeling low utility items into budget models. The classic essential versus non-essential partition, leaving essential holding only the terms whose cumulative potential can still beat the threshold. If your corpus were bigger and you lowered K, baseline MCS would rise and budget would shrink, converting more terms into mandatory contributors. The printout reports a 0.62 minimum competitive score with only skipping marked as core, meaning BM25 is safe to treat as optional cap space. Next, we convert those term-level caps into per-document base scores and optional caps. This bookkeeping tells us, before scanning optional postings, whether a document can possibly enter the top K. This snippet turns those abstract bounds into per-document skip signals, which is the bookkeeping MaxScore uses before scanning postings. Optional holds the relaxable terms. OptCap measures their combined upper bound per document. And base score sums actual contributions from essential hits collected in hits. By storing base ops alongside base score, we know exactly how many computations have already been paid for before touching optional postings. Skip flags compares each base plus OptCap against baseline MCS. So if you widen the threshold, for example by increasing K, more entries would flip to false and require full evaluation. The printed dictionary shows that only document 2 must process optional BM25, confirming where pruning effort still matters. Finally, we run the MaxScore evaluation loop. This step mixes guaranteed contributions with guarded optional checks and only scores optional terms, while a document might still beat the current threshold. This example executes the MaxScore evaluation loop, mixing essential scores with guarded optional scans to realize the pruning savings. It starts with K and THR, adds each document's base score while accounting for the base ops already spent, then skips early whenever the walrus-assigned remaining cap cannot beat the running threshold. The generator over optional terms ensures we only pay for BM25 when the document actually contains it, and each subtraction from remaining tightens the break condition mid-loop. After inserting each candidate, we update THR and materialize TS so we can compare against the exhaustive baseline. Raising K would delay threshold tightening and shrink the saved count. The output shows MaxScore still returning documents 2 and 1, but with one fewer scoring touch than the exhaustive run. Quick recap. MaxScore keeps the exact top K while avoiding a lot of needless BM25 math. Reach for it when queries have multiple terms and many candidate documents, and you care about CPU or latency. One caveat: you must compute safe per term upper bounds and track bookkeeping correctly, or you risk pruning a winning document. Next step: run the same pipeline on a larger corpus and tune the BM25 K1 and B parameters to see how those settings change pruning and score gaps. That single change usually shifts how many terms become essential and how much work MaxScore can save. If short, practical IR helps, subscribe and watch the IR videos.